nanoHUB-U online instruction.
Hello and welcome back to nanoHUB-U's Introduction to Bioelectricity. I am Professor Pedro Irathoki at Purdue University, and we are in week 6, numerical methods of solving differential equations. So the goal in this week is to take the Hodgkin-Huxley equation that we learned about in week 4 and find a way to solve it. So it is a differential equation of the type that does not have a continuous analytical solution, and so we're learning about numerical solutions to approximate the analytical solution. In the first lecture of this week, we talked about what is the difference between continuous and discrete time solutions, and what are the sorts of things we need to be careful about when we're using or we're arriving at numerical solutions. Things like, for example, aliasing and sampling rate. In the next lecture, we talked about the Euler method, and we talked about the Taylor method as the first two methods to begin to actually solve differential equations using these numerical approaches, where the Euler method had the advantage of simplicity and the Taylor method had greater complexity but greater accuracy. And we also talked about sources of error, specifically truncation error and round-off error, and we mentioned also numerical instabilities. In this lecture, we're going to talk about the Runge-Kutta method, a third method and the last method we'll learn about in this course for solving differential equations, and one which presents many of the advantages of the preceding methods that we discussed. So in the Runge-Kutta method, what we're doing is instead of using a single slope, we're using a number of slopes. But before we get that far ahead, let's go through it step by step. So the Euler method had the advantage of simplicity. The next point is in the solution of an equation is equal to the current point, y sub n, plus the slope, which is y sub n prime. It's the given equation we're trying to solve, multiplied by the distance to the next point. So we assume a straight line between points, and so it's just the rise multiplied times the run to get to that next point gives us the delta, and we're done. The Taylor method says, well, we know that that's not true. It's probably not a straight line between points. So in addition to looking at the slope, which is that straight line approximation, we're going to look at the second derivative, which tells us how the slope is changing, and the third derivative, which is how the slope's change is changing, and so on and so forth, to get a much more accurate picture. But the disadvantage of it is that you get that accuracy at the cost of having a much greater complexity, and now you have to do a whole bunch of calculus because you're given y prime, but you're not necessarily given y double prime and triple prime and so on. You have to find those, which assumes that you have a differentiable function. Not all functions are differentiable, and if you have a non-differentiable function, you cannot solve it using the Taylor method. So to improve on Taylor, we want to increase the accuracy of our solution without increasing the number of derivatives. And that is what the Runge-Kutta method will do. How does it do it? Runge-Kutta calculates the slope as an Euler. So it says the slope, in Euler, the slope is equal to y prime. In Runge-Kutta, the slopes are denoted by k because there are going to be many slopes that we're going to calculate, depending on the order of the Runge-Kutta method. A first order will have one slope, it'll be Euler. A second order will have two slopes. A fourth order will have four slopes, and so on. So k1, in a first order method, k1, the slope, is equal to y prime, evaluated at the current point, t sub n and y sub n. Ordinarily, at this point, using Euler, we would now calculate the next point, y sub n plus 1, which is equal to y sub n plus h times k1. That's the Euler method. Instead, what we do in the Runge-Kutta method is we then calculate the slope halfway between the y sub n value and the y sub n plus 1 value. So halfway between this current value of time that is known, initially it's the initial condition, and the next value, which is t plus h, halfway in the middle, we're going to calculate what the slope is. And that slope is going to be y sub n plus, or that halfway point is going to be y sub n plus h over 2 times k plus 1. And once we know what that halfway point is, then we'll calculate a second slope. So that second slope is equal to y prime, the derivative, evaluated at that halfway point, which is t sub n plus h over 2 instead of t sub n plus h, and y sub n plus h over 2 times k1 instead of just y sub n plus h times k1. Okay. And then we're going to use a weighted average of those two slopes, k1 and k2, and that weighting of that average is going to be done, in this case it seems a little trivial because we're going to drop k1 and we're going to keep k2, but you'll see how the weighting works a little bit better when we do higher order Runge-Kutta methods, and we're going to do a weighted average, and now we're going to calculate y sub n plus 1 using that weighted average slope, which is really that second slope. But remember, we use the first slope to get that second slope. So you can't just go right to that second slope. And that should also remind you of the last lecture where we talked about how important it is to do things in order and not to skip steps. So in this case, we have an initial condition. We know what y is at n, and we want to solve for y at t equals n plus 1. So we begin by calculating the slope k1, which is just y prime evaluated at n, and then we multiply that out times h over 2 to get the halfway point between y at n and y at n plus 1, and we solve for the slope at that halfway point. So we use k1 to find the halfway point. We calculate the slope at the halfway point, and then we say, you know what? The slope in the middle between n and n plus 1 is probably a better guess as to the average slope than the slope at the beginning. And so we're going to use that slope instead of k1, and we're going to calculate y sub n plus 1 as k2 times h plus y sub n. That is a Runge-Kutta solution. To improve the Runge-Kutta solution, all we have to do is increase the number of slopes. Instead of taking one extra slope like we did just now, we can take 3, 4, 5, however many you want slopes. With the more slopes you take, the greater the accuracy. And note that at no point have we taken a derivative. So there are no additional derivatives. And it turns out that if you do this and you look at all the different orders of Runge-Kutta, you find that the fourth order Runge-Kutta method is a sweet spot that gives you an enormous amount of accuracy without an enormous amount of computational complexity. And so the fourth order Runge-Kutta method is the one that we're really going to learn about in this lecture, and the one that we're going to use to solve the Hodgkin-Huxley equation in this course. So let's take a closer look at that. In the fourth order Runge-Kutta method, you're going to calculate, as you can expect, 4 slopes. So you have the same basic problem that we've had before. You have y, and you know what the analytical solution is here, and this just gives us a sense about how close our approximation is to that analytical solution. And in the real world, you wouldn't know what that analytical solution is, and that's why we're using these methods. We're given what the starting value is. We know what y is at n, and we want to find y at n plus 1. So we start out with the Euler method by calculating k1. That's the slope at y sub n, and that slope is going to give us the halfway point. And that halfway point is going to be y prime evaluated at the beginning, which will give you k1 multiplied times h over 2. Then using that halfway point, we'll calculate the slope at the halfway point, which will be y prime at n plus h over 2, and we'll get k2. Then we'll use k2 from the beginning to calculate k3, the slope at the halfway point again. And these two slopes will be different. K2 and K3 will be different, even though they're both taken at the halfway point, because y prime is a function of both the dependent and independent variables. It's a function of both y and t. And so the halfway point in t is the same for both the calculation of K2 and K3. But the yn point is different, because in order to calculate the y value, or in this case, the membrane voltage V, we used, to calculate for K2, we used K1, but for K3, we used K2. So we use K1 to get K2, we use K2 to get K3, and once we have K3, we use it to calculate not the halfway point, but the end point. And then we calculate K4. So we're measuring what the slope is at the beginning, what the slope is in the middle, twice, using two different guesses of the slope, and then the slope at the end. So we have slope K1, slope K2, K3, and K4. Let's go through that all one more time. So, in the Euler method, what we do is we calculate the slope at the point we're at, and then we multiply that slope times the distance to the next point, and we have what our next point is. In the fourth order Runge-Kutta method, we calculate the slope at the point that we're at, and then we use that slope to calculate the halfway point. Then we calculate the slope at the halfway point. That's K2. Then we use K2, starting back at the beginning, to calculate the halfway point again. And then we calculate the slope at the halfway point, but the halfway point is different because we use K2 to get there instead of K1. So when we calculate the slope again, we're going to get a new value, and we're going to call it K3. Then we go back to the beginning. We use K3 to calculate the next point. Not the halfway point, but not y sub n plus h over 2, but y sub n plus h. We calculate the next point, and then we calculate the slope at that next point, and that's K4. So we have 4 slopes. K1, which is calculated from y prime, just as we did in Euler. K2, which is calculated at the halfway point, which we found using K1. K3, which is calculated at the halfway point, which we found using K2. And then K4, which is calculated at the next point, and we found using K3. So K2 is using K1, K3 is using K2, K4 is using K3. They build on each other, and now we have 4 guesses as to what is actually happening between y sub n and y sub n plus 1. And we take a weighted average of those 4 slopes. And the weighted average is that K bar, the average slope, is going to be equal to K1, the first slope we calculated, plus 2 times K2, the second slope we calculated, plus 2 times K3, the third slope we calculated, plus K4. Divided by 6 to normalize it, and we end up with our K bar, our average slope. And that gives us a sense of not just a really accurate understanding of what is going on at this first point, which is what Taylor does, but rather an understanding of how the slope is changing as we progress from the first point to the next point, which is what the Runge-Kutta method does. And there's no additional calculus. So the next question is, if that's how you solve Runge-Kutta, and it seems complicated, but once you write it all into your algorithm, it's very straightforward. And if you want to solve lots of points, it's fine. You just increase the size of your for loop, or the number of times you run through your for loop. The next question is, all right, well, this is all fine and well, but all we've solved so far are first-order derivatives. The whole reason why we're learning how to use numerical methods is so that we can develop a solution to the fourth-order Runge-Kutta equation describing the membrane voltage as a function of distance and time within a neuron. So how do we use these first-order methods to solve second-order methods? And the answer is actually simpler than you might expect. The way you solve a second-order ordinary differential equation, for example, is by reducing it to a system of first-order ordinary differential equations by using new variables that we can define however we like. So for example, let's say you had an equation that said that the second derivative of y double prime, is equal to the first derivative of y prime, plus y, plus t by some constant c. Okay? Then we can define 2 new variables, u1 and u2, where u1 is equal to y, and u2 is equal to y prime. And then, by substitution, we can rewrite our ordinary differential equation such that u1 prime is u2, because u1 is y, so u1 prime is y prime, and we defined y prime as u2, so that's just an observation. u1 prime is u2, and then u2 prime, where u2 is y prime, so u2 prime is y double prime, so u2 prime, single prime, is equal to y prime, which is u2, plus y, which is u1, plus t, plus c. But these 2 equations are first order, right? It's u1 prime and u2 prime. There are no second derivatives in here. So just by rewriting this equation, which has a second order derivative, in this way, we arrive at a system of first order differential equations, which we can solve the way that we've been doing with Euler, Taylor, and the fourth order Runge-Kutta method. And in fact, this is exactly what we're going to do in Hodgkin-Huxley in the next lecture. But before we get there, let's go through some examples here so we can see how the progression happens. So using Runge-Kutta for a second order ordinary differential equation, or an nth order, or m as in Mary, mth order differential equation, where we have up to m equations, we solve every k, then every u, and then we solve the next point. So for u1, which in this case is going to be y, and then u2, which is going to be y prime, and if we had a third order ordinary differential equation, we would have a u3, which would be y double prime, and if we had a fourth order, we'd have a u4, which would be y triple prime, and so on down the line. We're going to have a series of solutions. So we're not just going to solve for y, we're going to solve for y, y prime, and so on, and we're going to get a whole bunch of extra information, which may or may not be useful depending on the equation that you're trying to solve. But at the worst case scenario, you'll solve for u1, u2, u3, and so on. We'll just throw away u2, u3, and on down the line when we're done solving. we still need to solve for them because we can't solve U1 without solving them all together. Again, remember, it's very important that we solve everything together in order and not try to solve one piece by itself, because they're all interrelated. So with the fourth order Runge-Kutta method, where we're trying to solve for capital N, N is in Nancy points from 0 to capital N minus 1, we're trying to solve a mth order, M is in Mary, order ordinary differential equation as M is in Mary functions from U1 to UM. The first step is to calculate the first slope, K1, for all of the equations, U1, U2, U3, all the way through U capital M. So the first slope is going to be K1, 1, 1. And the subscripts are going to be very, very important here, and to keep them straight, especially when you start coding this in your semester projects. So the subscripts are critical. And in this case, the first subscript refers to the slope number. This is slope number 1 at n equals 1. This is the first point at or for equation u sub 1. That's the third subscript. So the slope, the number that you're at, and the equation that you're trying to solve. So first you're going to solve the first slope for the first point and the first equation, K111, which is just U1 evaluated, right? Because remember, U1 is just y prime. It's U1 evaluated at this value. That'll give you the slope. The second thing you're going to do is solve the first slope, K, or this is capital U, right? This is capital U1 is the function. The second thing you're going to do is you're going to solve the first slope at the first point for the second equation, U2. And then the first slope at the first point for the third equation, U3. And then the first slope at the first point for the mth equation, M is in Mary. And then you've solved all of your K1 values for all of your different equations. Then you're going to go back and you're going to say, well, we have our first slope. Now we need our second slope. So we're going to solve the second slope still at the first point for the first equation, which is evaluated at h over 2. The second slope for the first point for the second equation, evaluated at the same place. The second slope, the first point for the third equation, and all the way down the line through the nth equation. Now what you'll notice is that you're evaluating these different derivatives, right, to get those slopes. You're evaluating these different derivatives. You're using different functions, u1 down through um. But the point you're evaluating them at is always the same. And for the previous one, for the first slope, it was the current time that you're at, or the current dependent or independent variable that you're at, plus the current values of each of those equations, u1, u2, and so on, where u1 is y and u2 is y prime, and so on and so forth. And capital U1 is y prime, and capital U2 is y double prime, and so on down the line. So you're solving these points at the same place for each one. When you go to the next step, step 2, and you're solving the second slope, now you're doing it as a function of h over 2, but you're using K111, the slope you calculated previously, and K112, the slope you calculated previously for the second equation, and on down the line. And this is why you have to do things in order. It's why you can't solve U1 by itself. You need to solve U1, U2, U3 down to UM for all slopes before the next slope, for all points before the next point, is because you use them to calculate the next points. And as you begin coding this, all of this will fall into place for you. So you calculate the second slope, and then you go in and you calculate the third slope, where the third slope is evaluated at using the second slope. And it's the third slope, the first point, the first equation, the third slope, the first point, the second equation, the third slope, the first point, the third equation, and down to the mth equation. And then you do the fourth slope for the first equation, the fourth slope for the second equation, fourth slope for the third equation, all the way down to the fourth slope for the mth equation. And now you have the 4 slopes for all of your equations. Now you can do a weighted average, and that's step 5, is you do the average slope still for the first point. We still haven't calculated what the next point is. For the first point for all equations. And you have K11 bar, where it's the first slope, or the average slope for the first point of the first equation, the average slope, the first point, the second equation, the average slope for the first point the third equation. So we've dropped the first equation, the first subscript, which told us what the slope number was, because now we have average slopes. And we go to step 6, which is we use Euler to calculate the next point. U2, the second point for the first equation, is U11, the first point for the first equation, plus h, the distance, multiplied times k11 bar, which is the first slope, or the average slope for the first point for the first equation, and that gives us the next point. And you do that for the second point, and the third, or the second equation, the third equation, and all the way down to the nth equation. So now we've calculated what our next point is, and we can repeat to calculate u sub n plus 2, and then u sub n plus 3. And it seems extremely complicated to go through these 7 steps. It's actually not. When you look at it, it all makes sense. It's all very methodical. And once you've written the code to do it all, well, it really doesn't matter if you have 1 ordinary differential equation or 15 ordinary differential equations, because that's a for loop too. So you have one for loop that solves all the points. You have another for loop nested within the first loop that solves for however many equations you have. And if you nest your for loops properly, it's really 1 page of code. And you can solve an nth order ordinary differential equation for n points, where m and n can be any number short of infinity. And so what we'll do in the next lecture is we'll begin using this to solve the Hodgkin-Huxley, and I'll show you exactly how to do it. And I'll see you then.